In this video, we're going to start talking about chemical kinetics. And we're going to start with just the idea of reaction rates, and that's how we measure the speed of a chemical reaction. It's just how fast are we making products. And chemists want to be able to control this reaction rate, generally to try and speed up reactions that might be too slow to do otherwise. Right? So what is a rate? A rate is simply a change in something over a change in time. And we know this from our everyday lives. When we're driving a car, our car is going at some rate, so many miles per hour. And in chemistry, it's the same idea. We're making so many products per second, per minute, per hour, so on and so forth. Right? So for chemistry, your reaction rate is either how much did my reactant decrease or how much did my product increase over a given period of time. And let's look at this for a simple reaction. H2 plus I2 goes to 2HI. Our rate is, and let's look at how to read this, delta is change. So the change in this bracket H2 means concentration of H2. Delta T means a change in time. And negative. Negative because we're losing H2, so that's why our rate is negative. Because this change in H2 is going to be negative, but our rate can't be negative. That's very important here. You cannot drive a car minus 60 miles per hour. So your chemical rate can't be minus concentration per time. It has to be positive. So H2 loses concentration. So that's why we put the negative sign here. To actually calculate this, it's just the concentration of H2 at some time point minus the concentration of H2 at our initial time point divided by those two time points. So when we're doing delta, it's always final minus initial. And again, if you have a negative number, most likely you just switched T2 and T1 somewhere. And we can look at this graphically as well. So here green is our change in H2 and red is our change in HI, which was our product in our reaction. And you can see that as the reaction goes on, the reaction rates actually change. So depending where you take your measurement from, as shown here in an example, you will get a different reaction rate. Because as we learned with the vapor pressure videos, eventually you are going to get to a chemical equilibrium where the change of the forward reaction making HI will be the same as the reverse reaction making H2 and I2. You'll be at equilibrium. All right. So since we can take a rate at any given point, we have different rates we can talk about. One is instantaneous rate. That is, on the curves we just saw in the previous slide, you just take the tangent or you just take the slope at any point. That's how fast your reaction is going on that time point. Those of you who have taken calculus already, don't worry, we don't have to do calculus in this course, but it is just the first derivative of your rate function. That's your instantaneous speed. We can also talk about average speed, though, and that is basically taking a linear approximation of our curve. We're just going to take a section of our curve, imagine that it's linear, and that's our rate. And you can see here in this graph, we have a bunch of different average rates, and they are slowing down. Just keep in mind, the bigger the time interval you take for your average rate, the more it's going to be different from the instantaneous rate at that given time point, and the more in error it's going to be when compared to the instantaneous rate. So all we've been doing here is looking at our change in H2, our change in time, and then we get our change in rate. So as I said during the slide with the plot on it, reactions will slow down as they proceed. You'll start making enough products, and pretty soon the amount of products you have are in excess, so they'll start making reactant. So eventually the slopes are going to be a straight line. Your amount of product is not going to change over time, and that's what it means to be at equilibrium. Or another case is that you just run out of reactants and the reaction cannot go backwards, and so it's just stopped. You can't go forward anymore. So let's look at reaction rates and stoichiometry now. And so for a lot of chemical reactions, each species in our reaction does not have the same coefficient, same stoichiometry coefficient. So for example, H2 here has a coefficient of 1. Remember, even if it's not shown, that's a coefficient of 1. I2 has a coefficient of 1. HI has a coefficient of 2. Excuse me. So in this reaction, what the stoichiometry is telling us is that for every 1 mole of H2O that we use, we make 2 moles of HI. Same thing. For every 1 mole of I2 we use, we use 2 moles of HI. Therefore, depending on what we're measuring, our rate will be different. We're making twice as much HI over the same time point as we're losing either H2 or I2. And we don't really want that. We want to be able to measure the rate and get the same rate no matter what species we look at. And so to be consistent with that, when we do our change in chemical species over change in time, we multiply that by 1 over our stoichiometry coefficient here. So for the reaction A plus B goes to C plus D, here's our reaction rate, where little a, b, c, and d are our stoichiometry coefficients. So let's take a look at this for our example reaction up here. We have rate is negative 1 over 1 because the coefficient of H2 is 1. Change in the H2 over some change of time, that's negative because we're losing it. That's also equal to negative 1 over 1. Coefficient for I2 is 1. Change in the amount of I2 over change in time, that's negative because we're losing it. That's equal to 1 over 2 now because our coefficient is 2. Change in the amount of HI divided by change in T. This number is positive because we're making it. And so with this rate, no matter how we measure the reaction, we should get the same rate every single time. And to measure these rates, inside of a lab, we have different instruments, but the instruments pretty much do the same thing. We either measure the color of the solution over time. If we're using gases, we measure the pressure over time, or we can measure how these molecules absorb light over time. But the basic idea is you need something that you can measure that correlates to your product, and you do that measurement over time, and that's how you know change in concentration over time. And that's it for this video, and I will see you in the next one.